Hi everyone. So in this session, I'm going to talk about amplifier modeling, okay, which is very important topic in entire analog circuit, right? So in amplifier modeling, basically we will take one practical real life example, okay, to explain you better, right? So the real life example which I'm going to take is the public address system, right? How to address million of public, okay? How to address million of public, right? Okay, address system. So what are the equipments we always use, right? So we are going to discuss about them only, right? But we will treat them as a black box, right? So the very first black box is going to be the microphone, right? So right now I'm teaching you, okay? So I'm using the microphone, you can see, right? And if my voice is at low strength, right? If my voice is at low strength, so you will not be able to hear my voice, okay? So we need kind of device, okay, which can enhance, okay, my strength of our voice, okay? So we are going to use the next black box, that is going to be the amplifier, okay? So we will see how we are going to model these amplifiers, how we are going to model this microphone, right? And at your end, definitely there should be one speaker, otherwise you will not be able to hear my voice, okay, what I'm teaching you, right? So there should be one speaker. So these are the three major blocks, okay, we are going to model in this lecture, okay? So the first block is going to be the microphone, okay, and second block is amplifier, and third block is speaker. So one by one we are going to take up, okay? So these are the black box, you can take it like that, okay? So the microphone, what is the job of microphone basically is, the microphone will convert, after all your voice is going to be the non-electrical quantity, right? So the voice is basically the non-electrical quantity, and the microphone will pick up your voice and it will convert non-electrical quantity to the electrical quantity, right? So the question will come in your mind is that why we are converting non-electrical quantity to electrical quantity, right? Amplifier is, an electrical device, right? So it will not be able to understand your voice directly. Suppose there is no microphone, I'm not using any microphone, right? So amplifier will not be able to understand what I'm speaking, okay? So we need microphone, right, at first. So if we are speaking something, so the voice will be picked up by the microphone, and then it will convert into electrical signal, right? So what are the electrical signal basically in electrical engineering? They are voltage or current, right? They are basically voltage or current, okay? So in the input of the amplifier, we need to convert our non-electrical voice to the electrical signal, right? They are voltage or current. They will be definitely time varying voltage or current, right? Because signal cannot be uh, you know constant, okay? Signal should be having time variation, okay, variation with respect to time, okay? So we are going to see how we are going to model the amplifier, right, with the help of electrical components, okay? And then we will go to understand how we can model amplifier, and at the end we will draw kind of amplifier, right? We will try to classify the amplifier based on the input quantity and the output quantity, okay? And we will see how many kinds of amplifiers are there, right? So the microphone here, you can see in the bracket, microphone can be modeled with the help of independent sources, what we have seen in the network theory, right? So you have already seen about independent sources. They can be the voltage source or a current source, So the voltage source can be what? The voltage source must be the practical voltage source I'm talking about, the practical voltage source, right? And there should be one series resistance associated with the voltage source, right? Then we can say this is going to be the practical independent voltage source, right? So the very first black box can be modeled, or microphone can be modeled with the help of practical voltage source, okay? If the signal is of voltage in nature, your signal can be of current in nature, right? So you can use the current source here, the practical current source, right? The practical current source is, and now you have to connect this resistance, right, in the parallel, right? You might have seen this kind of independent sources, okay, in your network theory, right? So these are the black boxes, right? So we need to model, okay, this microphone with the help of practical independent sources, okay? So they have got certain name, okay, in the history, right? So we need to give certain name to these independent sources. Okay, so as I said that the microphone can be modeled using independent sources, right? Okay, so what are the well-known equivalents we know in the network analysis, right? So can you tell me what are the well-known equivalents? They are the Thevenin equivalents, okay, and the Norton equivalents, right? Any big network, anything can be modeled, any black box can be modeled with the help of VTH and RTH, right? With the help of VTH and RTH, okay? Any big network, you might have seen the network analysis. If you're looking back to the network, so entire network is looked at, okay, and looked as, you know, single voltage source and one series resistance, okay, VTH and RTH, okay. So here microphone can be modeled. After all, your microphone is going to be a source, okay. This is a source, okay, which is going to be picking up your voice, okay, and will convert into the voltage or a current, right? Definitely it would be the time varying current and voltage, okay. So microphone will be modeled as independent sources, you have to keep in mind, and they have got certain name. You will refer certain reference books, you will find that the microphone can be modeled with the help of Thevenin equivalents and the Norton equivalents. How does Thevenin equivalent look like? We know that Thevenin equivalent look like this, okay, simple. Vs and Rs we can say, okay. You can also say Vs means VTH and Rs means RTH, right? But we are talking about source, right? So we are writing Vs and Rs, and the Norton equivalent can be represented like this, right? Is, and in the parallel there should be Rs, right? This is Norton current, you can say, right? So any black box in the network analysis problem, we have seen that already, you might have seen in the class, right? So any network is given, right? You can treat that unknown network as VTH and RTH, okay, or you know, short circuit current and the Norton resistance, right? Or Norton current and Norton resistance in parallel, right? So as we have seen that the microphone can be modeled with the help of independent sources. So my first black box has been modeled successfully, right? So this is how we represent Thevenin equivalents and the Norton equivalents, right? So these are the representation we use always, okay, for representing microphone, okay. So in any equivalent circuit in future, you will find that your input signal will be given with the help of these or input signal will be represented with the help of voltage source or a current source. They should be the practical voltage source or practical current source, right? That's why I'm giving the name Thevenin equivalent or a Norton equivalent. So if somebody is going to ask you, okay, how can we model microphone? So you have to directly tell that we can use Thevenin equivalents, what we have studied in network analysis, and we can use Norton equivalent depending upon the nature of the input signal, right? If we want to amplify voltage signal, so we need to connect voltage source, right, or Thevenin equivalent. If we need to amplify, okay, the current signal, right, if we want to apply to the amplifier, right, the current signal, so we need to use what? The Norton equivalents, right? Okay, so the very first block, that was the microphone, okay, we can model with the help of independent sources. So I hope this is understood to you, right? Now as we know that the load, okay, we will discuss about amplifier, what is amplifier, right, and how we can model the amplifier, and how many kinds of amplifiers we need to study in entire analog circuit, right? So the load, or we can say the speaker, right? This is the speaker basically, right? This speaker can be represented with the help of load, and simple load you can use, that is going to be the resistance, simple load resistance, right? So with the help of simple load resistance, okay, you can represent, you can model the speaker, right? At your end, without a speaker, you cannot understand what I am speaking, right? Okay, so this is how we can model a microphone, and this is how we can model load, okay? So microphone can be modeled with the help of independent sources, and the independent sources, there are well-known equivalents, are there two well-known equivalents, right? First one is going to be the Thevenin equivalent and the Norton equivalents, right? So you will always see in the equivalent circuit that there is one voltage source along with this, you know, series resistance current source along with the one parallel resistance, okay, connected to it, right? Okay, so this is what the equivalent of Thevenin equivalent and the Norton equivalent, which can be used to model microphone. Okay, now we will talk about amplifier. Okay, so what is an amplifier? So amplifier is basically the electrical device, okay, which enhances the strength of a signal, right? Suppose I'm speaking something, right, and you're not able to hear me, right? So you will say that, sir, what you are speaking exactly, right? So I will say there is no amplifier. So how can I amplify my voice? Okay, my voice is will be always at low stereo or at low strength, right? Suppose there are million of people in front of me, right, and I want to address them, okay? So without microphone we can't address them, right? So we need a microphone, we need amplifier, okay? Otherwise my voice will not be able to reach to million of people, right? So amplifier is the device. The job of amplifier is going to be the amplification, right? The job of amplifier is going to be the amplification, right? This is the operation which is done by the amplifier. So amplifier is the device which enhances or boosts up the strength of a signal, we can say. So my signal is basically what? The voice signal, okay, which is going to be picked up by the microphone and will be applied across the amplifier, and amplifier will understand if it is voltage or current, okay? If it is non-electric quantity, it is not going to be understood by the amplifier, okay? Because in the microphone there would be some transducer, right? And transducer will convert non-electrical quantity into electrical quantity, right? At the same time, in the speaker also there would be some transducer. We can say that there would be process transducer, okay? There are different kind of transducer. Instrumentation engineer understand, okay, about transducer, right? So we need to only understand the definition of transducer, or a job of transducer is to convert non-electrical quantity or one form of energy to, or you can say non-electrical quantity to electrical quantity, right? So the amplifier is basically what? The electrical device which will enhance the strength of a signal, right? Okay, so here you can see this is going to be just a black box again, and I'm not talking about any particular amplifier, such as with the help of bipolar junction transistor or a MOSFET in future we will study. So any amplifier will be having input signal, okay, and it will give you the output signal, right? So what we want some mathematical understanding, okay? How does amplifier amplify the signal? So this K will be there, okay? So suppose in the input there is the voltage, okay? Voltage is there in the input of the amplifier. So your output, what we expect here is that your output should be K times of V in, right? And if the input is going to be the current, right? So what we expect here is that I out should be the K times of I in, right? K times of I in, okay? So amplification is basically, if we talk about in math, so amplification is going to be what? Simple multiplication by the scalar constant K, right? So this K will be having different dimension, we will see, or sometimes it would be having no dimension as well. So if the input signal is going to be voltage, so the output signal is also going to be the voltage. So V out is going to be K times V in. I in is going to be what? I out equal to K times of I in. Suppose input is going to be V in, voltage only, and output is going to be, okay, current, right? So it should be K times of V in, right? There can be four possibility basically. And if the input signal is current, right? So output signal is going to be the voltage, so it must be K times of I in, right? Okay, so these are what? These are the output what we expect, right? So mathematically, if we see that if we are applying certain input, right, to the amplifier, it is getting amplified, right? Means that there is some multiplication by certain factor to the input signal, right? So we are getting V out equal to K times of V in, means your output voltage is depending upon input, right? Means your output port, we can say, right? Your output your output is being controlled by the input, right? Now you are getting you might be guessing how we can model the amplifier, with the help of which component, electrical component, we can model the amplifier, right? So let me tell you one of the very important application of controlled sources, okay? Controlled sources, right? So the amplifier can be modeled with the help of dependent or controlled source, right? In the network analysis, you might have studied about dependent sources, right? Or a controlled sources. Why? Because output voltage or output port, you can say, output part is being controlled by the input part, right? So here the controlling parameter is gonna be the input, okay, and which is being controlled by what input port, right? So you have to understand that amplifier can be modeled with the help of dependent sources, okay? So you might be bonding now, right? This was the what secret, okay? The application of major application, if somebody is going to ask you what is the major application of dependent sources or controlled sources in network analysis, what we study, so you can directly tell them what the amplifier, okay? To model kind of amplifier, we need to use dependent sources or a controlled sources, right? So you have to keep in mind this, okay? So depending upon the nature of the input and output signal, right? So as we have seen that the signal, input signal can be voltage or a current, right? Output signal can be voltage or a current, right? Simply it will be multiplied by certain constant k, right? Okay, so depending upon the nature of the input and output signal, right, either voltage or current, right, amplifiers can be modeled as four kinds, right? So we can say there would be four kinds of amplifier. How we are saying that there can be four kind of amplifier? Just like there are four kinds of controlled sources, as we are treating controlled sources, okay, as amplifier, right, we are modeling our amplifier as dependent sources, right, with the help of dependent sources. So we can say that there will be four kind of amplifiers, okay, depending upon input nature, nature of the input signal or nature of the output signal, okay. So here you can see the first kind of amplifier is gonna be the voltage controlled voltage source, right? This controlled, voltage controlled means the input is going to be what? The voltage controlled means here the input is gonna be what? And the voltage control means what? Input is going to be voltage, okay? And the voltage source means what? The output is going to be voltage signal only, right? So voltage control voltage source is going to be our first kind of amplifier, right? And the second kind of amplifier we can say is current control current source, right? So here the input is going to be what? I in, okay, and the output is going to be I out, right? So input and output both are current in nature, right? And next we can have the combination like current control voltage source, okay, and the fourth kind of amplifier we can say is voltage control current source. So there are four kind of dependent sources we have studied in network analysis, okay. So we can say that there can be four kind of amplifier, right? So now I'm sure that you might have understood what is the major application of dependent or controlled sources, okay. So electronics and communication engineers, okay, they better understand that the what is the real use of dependent sources, okay. Without amplifier we can't survive, okay. So in fact in entire analog circuit we always talk about amplifiers and amplifiers, okay, be it bipolar junction based amplifier or metal oxide semiconductor based amplifier, okay. So we will talk about them as well, but this is just a fundamental, okay, fundamental of amplifier. So there are four kind of amplifier. You have to always keep in mind depending upon the input nature of the signal and the output nature of the signal, okay. So the very first kind of amplifier what we are now going to model, okay, as a whole, because we have seen the microphone can be modeled with the help of what? Microphone can be modeled with the help of dependent sources, or we can say Thevenin equivalent or a Norton equivalent, and load can be modeled with the help of resistances, right? And also we have seen that the amplifier can be modeled with the help of dependent sources, right? So the very first kind of amplifier what we are going to study is the voltage controlled voltage source, okay. So once you will understand how to draw the equivalent of voltage controlled voltage source, so you would be able to draw further three kind of amplifiers your own, right? But I will be explaining all of them, right? And we will also summarize at the end, right? So there would be, you will find another way of classifying the amplifier, right? Let us see. So voltage control voltage source, okay, it is also known as the voltage amplifier. Why we are saying voltage amplifier? because the input signal is voltage and the output signal is also voltage, and my objective is what? My objective is to get V out equal to K times of V in. What is my objective? We need to get V out equal to K times of V in, or you can say that K equal to what? V out upon V in, right? So what is the dimension of K here? The dimension is, K has no dimension, right? Because voltage upon voltage means what? Dimensionless, right? So as it is a voltage controlled voltage source, so it will give you the voltage gain here. You can say voltage gain AV. Okay, so voltage gain we can measure. Okay, we can find out voltage gain from the voltage controlled voltage source amplifier, right? This parameter we can calculate. So it is known as voltage amplifier, and voltage amplifier will be giving you according to the dimension. It is a dimensionless, right? So output upon input, okay, output signal upon input signal will give you the voltage gain, right? Okay, so this is how the controlled controlled source look like, right? So across this we can say that we want what? We want V out, right? V out should be equal to K times of V in, right? So why we are saying it is a voltage controlled? After all, this is a what? This is voltage source, right? Because there is a plus and there is a minus, right? And this always we know that we sometimes we can represent controlled sources with the help of circle and K times of V in, no problem, right? But usually we take or we use, we can say, the diamond shape, okay, to represent control sources, right? So this is kind of amplifier, right? But without microphone and the speaker, or we can say without Thevenin equivalent or a Norton equivalent and the load, your amplifier is alone, okay, it is useless, right? So you need to connect source first, okay, then the amplifier and then the load, right? So these are the three major black box we need to understand how they are being modeled, right? So this is going to be our first kind of amplifier, and as you can see here, this is going to be our objective to obtain. V out should be equal to K times of V in, right? So the input is what? The voltage control, right? So the input should be voltage, right? And voltage source, right? So output should be voltage again, right? Okay, so in the output what we are going to use? This symbol, right? So if the input signal is voltage, so we are going to use here the Thevenin equivalent, that is going to be what? Vs, right? And there should be one source resistance, that is going to be Rs, right? Okay, so this is a part of what? This is the microphone or source, we can say, okay. This from here to here, what is this? This is source, right? Now as we know that any amplifier will be having its own input resistance, okay, any amplifier will be having its own input resistance, and any amplifier will be having its own output resistance, right? So here we can say that, here let me use different color to highlight this, right? So this is the amplifier resistance, right? This is going to be the amplifier resistance, okay. So remember that any amplifier would be having its own input resistance and output resistance, right? Input resistance and output resistance, okay. So R in, so here we are going to take V in, okay. This is going to be the the input signal which is being applied across the amplifier, right? Now as we know that the output signal should be what? The voltage, okay, only. So here we are going to use voltage source, right? And what kind of voltage source we are going to use? As we know that the amplifier can be modeled with the help of controlled sources, so we are going to use this. So this is going to be your K times of V in, right? Okay, now as we know that any amplifier should be having what? Its own output resistance, so there should be R out, right? Okay, so this resistance should be connected in the series, because this is after all the voltage source only, okay, no matter it is a what? Controlled source, right? So you have to always connect resistance in the series. Now we can represent load, okay, we can represent speaker as a load, okay. Now so you can see here from here to here, okay, this red part is going to represent amplifier, right? From here to here this represents was source, and from here to here it represents load. So these are, there was three major blocks, right? And we are successfully modeled now entire amplifier equivalents, right? So this is going to be your source. Okay, this is going to be your source, which will pick up your voice, will convert into electrical signal. Okay, be it voltage or current, right? And the first kind of amplifier is the voltage control voltage source amplifier or a voltage amplifier. So we are connecting Thevenin equivalent here, and there is a resistance. Okay, Rin. Okay, it's a resistance, input resistance of the amplifier, and we will try to decide what can be the input resistance of voltage controlled voltage source amplifier, right? So we will see according to our requirements, right? Okay, so I hope this equivalent how I have drawn is understood by you. Now what we want is entire signal should be applied to the amplifier. We don't want any signal, we don't want the signal to be dropped across this RS, right? Why? Already my voice is at low strength, right? And we want amplifier to amplify my voice. If my voice again is going to be what the strength of a voice is going to be lesser, you know, across these areas, then you know my purpose will not be fulfilled, right? So what we want here is we need to keep this RS, we need to keep this RS as low as possible. If the resistance will be low, so the voltage drop across this resistance will be less, right? So my objective is what? My objective is we want, okay, you have to keep in mind that we want Vin equal to Vs. What we want? Vin equal to Vs. So this Rin should be far greater than Rs, right? My Rin should be far greater than Rs. This is our requirements, remember always, right? If there is a voltage control, okay, and we want entire signal to be applied across the Rin, right? So Rin should be very high, okay, Rin should be very high, and in fact open you can say, or infinite, ideally infinite, but it should be very high. So if someone is going to be asking you what is the input resistance of voltage controlled voltage source, what you will say? You will say always it should be high, sir. Okay, because we want Vin equal to Vs, right? So this Rs should be very this Rs should be kept at very low value, right? Okay, so you can say this Rs can be made, you know, 0, okay, or as low as possible, right? But you can't make it 0 because it will not be the practical voltage source then, right? Okay, so this is our requirement. Now in the load end, what we are measuring here is the output V out, right? So what we want here is we want V out equal to K times of V in, right? This is our requirements, right? We want always, we want to calculate this V out equal to K times of V in, right? So if this K times of Vin is going to be what? Going to be having this R out is going to be having some drop across this, right? Then you cannot get V out equal to K times of Vin, right? So again R out should be what? R out should be very low, right, compared to RL. Okay, so what you can say here is that RL should be very high compared to R out. Okay, so here you can say Rin should be what? Rin should be high. Okay, and here R out should be what? R out should be low. If the resistance will be low, as we know in the from the network analysis, if the resistance is going to be low, the voltage across the resistance, the voltage drop across the resistance will be low, right? So we will be able to achieve our objective. Okay, so now according to the requirements, right, we are able to decide what can be the input resistance of the voltage control voltage source amplifier, what can be the output resistance of the voltage control voltage source amplifier, right? So if someone is going to be asking, right, in fact in the examination many times, you know, from the amplifier modeling, right, they have asked the question that voltage control voltage source or different kind of amplifier, right, what can be the input resistance, what can be the output resistance, right? In fact this lecture is going to be very helpful to understand entire feedback amplifier, right? You would be able to identify, okay, what kind of feedback is there in the amplifier, right? But right now we are talking about only unilateral amplifier. I mean the energy flow is from input to output, there is no feedback. I mean I'm not taking any part of the output and connecting to the input, right? You can see here, right? So I have just taken three major blocks, the microphone, the amplifier and the load, and successfully we have drawn the equivalent of voltage controlled voltage source amplifier, right? Okay, so here you can see this is going to be the actual picture what we have drawn over there, right? So this part is going to be the source, right? This part is going to be the source, and this part is going to be your amplifier, okay? And this part is going to be the load, okay? So there are three major blocks, right? This was the three block here, right? This was the microphone, this was the amplifier, and this was the speaker, right? So we are successfully modeling what, with the help of Thevenin equivalent. If the signal is going to be voltage in nature, so we'll use voltage source here, and this is going to be the amplifier resistance, input resistance. This is going to be R out, you can say, okay? The output resistance of the amplifier, okay? And now we are able to decide, okay, whether input resistance will be high or low, right, depending upon our requirement. So what we want here, Vin equal to Vs, right? So we can say that Rin should be far greater than Rs, right? Means that the input resistance should be high, or ideally you can say infinite, right? And any voltage source will be having what, always low resistance. Internal resistance should be low. Any voltage source will be having low resistance. After all, this is a voltage source, okay? And it is also a controlled source. You can see here k times of Vin. But here what we want here is V out should be equal to what? V out should be equal to k times of Vin. We don't want any drop across this R out, right? So RL should be what? RL should be far greater than R out. So what we can conclude from here is that the output resistance of voltage controlled voltage source or voltage amplifier must be low. And here what we can conclude that Rin should be high, right? So these are the two very important conclusion, right? Okay. And one more thing is that let me erase this. Okay. So one more thing is that your output will be always independent of the load RL, right? Always independent. You can see here we are using RL, but my output is not depending upon RL, right? So always keep in mind that what you have to keep in mind that the output V out, right, is always independent of load, okay, RL, right? You have to keep in mind that this is one of the important notes. So I hope how to model the amplifier and how to decide the input resistance and output resistance of the voltage amplifier you have understood, right? So what you have to keep in mind that, or what you have to remember for the gate examination here is that if input signal is what, the voltage, right? So you have to consider that is voltage controlled, okay? Your output will be controlled by voltage only, right? So the voltage controlled, right? So if somebody is going to ask you what voltage controlled voltage source, right? So what is going to be the input resistance of that? So you can say high, sir, okay, high practically, right? Practically. And you can also tell them the requirements, right? So ideally input resistance must be high or infinite. So you have to keep in your mind one kind of convention that if there is a voltage control, means the resistance will be high. If there is a current controlled, okay, if there is a current controlled, or in future you will see that if there is a current control, right, so the voltage should be low, right? Input, okay, input part will be always controlling, okay, remember. So here the Vs, okay, what Vs represent here is that the amplifier, right? So amplifier is being modeled with the help of control sources, right? So this voltage source is basically the control source, right? So if Vs is there, we know that any voltage source will be having internal resistance what, low. Ideally we can say 0, right? So you have to keep these two important facts, right? So that's why I have written in the slide that important to remember, right? So for the examination sake, right? So if there is a VC, Rin will be infinite, okay? Blindly you can tell anyone, right? If there is a Vs, output resistance will be always what? Output resistance will be always low or 0, you can say low, right? Practically, okay, right? So example of voltage control voltage source, right? Definitely you might be wondering what are the examples of voltage control voltage source. So right now I'm not going to discuss in detail, just I'm going to tell you a few examples, right? So based on the input resistance and output resistance, can you tell me what kind of amplifier you have seen in your real life which is having input resistance high and the output resistance low? So I think one very versatile op amp, amplifier you might be knowing or you might be familiar is that operational amplifier. You know, inherently operational amplifier behaves like a voltage control voltage source, okay? Because operational amplifier is having ideal input resistance infinite and the output resistance zero, right? So this is one of the best example, right? And in fact in entire analog circuit you will find that op amp is one of the very versatile structure, right? And many questions we can expect from this topic, right? If you see past 5 or 10 years of question paper, you will always find op amp questions, right? So in fact in entire industry also, in analog industry, op amps are being used, right? Okay. So operational amplifier inherently we have like voltage control voltage source, right? So how we are able to decide op amp behaves like VCVS? Because of its resistance, input resistance and output resistance, right? Okay. Ideally, any ideal op amp is having few properties, okay? Op amp will be having infinite resistance, okay, input resistance, and zero resistance, okay, output resistance, right? You have to keep in mind, okay? So this is going to be our what? This is going to be the basic equivalents. You can see here in the op amp. I'm not discussing right now. We will discuss op amp in the different in the different session, right, or a different class. Okay, so that op amp is one of the very big topic, right? Okay, so here we always apply the difference, okay, to the op amp, right? Op amp does not take particular signal. It will always take the difference, right, so that it can cancel the noise effect, right? Okay, so here you can see this is going to be R in and this is going to be R out, okay, and its equivalent is being matched with the voltage control voltage source. Okay, here you can see in the output what is there, voltage source, right? And here in the input what is there, voltage controlled. Okay, so voltage control voltage source, depending upon the input we can say voltage control, depending upon the output, okay, what kind of source you are using, we can say voltage source, right? Okay, and second kind of example, okay, we need to understand that the common collector, okay, common collector amplifier, or you can say that the emitter follower, sometimes we call this as emitter follower, right? Okay, when we will study about common collector amplifier using BJT, right, in future, okay, so we'll understand how common collector amplifier works and how it can work as voltage control voltage source. Okay, but for the time being you can decide based on the input resistance and output resistance, right? If you know the specification, suppose you have the data sheet, right, and somebody has told you that the amplifier is having high resistance, right, high, right, this is 9 mega ohm, right, and the output from is taken from here, right, in case of common collector, right? So if you see the output resistance, that is 8 ohm, right? So compared to 9 ohm, 8 ohm is very less, right? 8 ohm is very less, right? We can say that looking at the value of input resistance and output resistance, we can say yes, this guy is what the voltage control voltage source, right? So these are the two important examples which I wanted to highlight here. So I hope after discussing how to draw voltage control voltage source and how to extract the information about input resistance and output resistance based on our need, right? As we wanted that V in should be equal to Vs, entire signal should be applied across the amplifier so that we can amplify the signal. Okay, so these are the two major examples you have to keep in mind, right? So always whenever we discuss something, it has some correlation, right? So try to recall that. Okay, right. The second kind of amplifier what we are supposed to discuss is the current control current source, right? So if you have understood the first kind of amplifier, that was the voltage control voltage source, so this is going to be a cakewalk then. I mean, it is going to be very easy, right? So the current control current source, right? It is also known as the current amplifier. It is also known as what? The current amplifier. So output should be current, right? And it should be k times of I in, right? So from here we can calculate k. K is going to be what? I out upon I in, right? I out upon I in, right? What is the dimension of k here? Dimensionless, right? So we can say that it will give you current gain, right? Current gain here, okay? So we can calculate current gain from the current controlled current source. So it is also known as what? Current amplifier, right? Okay, so current gain, right? So in future you will find that current amplifier is also known as current buffer, right? And voltage amplifier is also known as voltage buffer, right? So this is how the current controlled current source looks like. Okay, you can see there is an arrow, so it is a current source, and there is a controlling parameter, that is current, right? That's why we are calling it current controlled current source. Okay, right? So this I naught, or you can say I out, is equal to k times of I in, right? This. Okay, now we need to draw the equivalent of current control current source. So the input is what? The current, right? So we need to use what? We need to recall Norton equivalent. Okay, that was current source, right? This is Is, and now where we need to connect the source resistance, it should be in parallel, right? Okay, this is Rs, right? And as we know that what we know that the any amplifier will be having its own input resistance, right? This is Rin, right? Okay, so we want In, okay, to be directly applied to the amplifier, so In should flow through this. Okay, earlier voltage was across the Rin, now In, what? In is the current, it should flow through the branch, right? Okay, now what kind of source we are going to use? We will be using current source, right? Okay, so this will be current control current source, right? K times of I in. Okay, now can you tell me where we need to connect the output resistance? It should be connected in the parallel, right? Because it is what? It is basically the current control current source, right? So current source should be having the resistance connected in parallel, right? Okay, now we can represent what? We can represent load. Okay, that is going to be RL, right? Okay, let me highlight everything here. From here to here it is going to be your source, right? Source. And from here to here, okay, from here to here, this is R out, you can say. It is going to be your amplifier, that is current amplifier, or you can say current control current source. And from here to here it should be load, right? Okay, so what we want here is that we want I out here, right? And now we need to understand what can be the input resistance of current control current source, what can be the output resistance of current control current source, right? So depending upon our requirements, we need to understand. What we want here is we want In should be equal to Is. What we want? We want In should be equal to Is, right? So we can write here, we want In should be equal to Is, right? Means that entire signal should be applied to the amplifier, right? So that your amplifier can do its own job, right? Okay, so what should be the Rs then? We don't want any current to flow through this Rs, right? So this Rs should be very high, right? This Rs should be very high, right? And this Rn should be very low. As we know from the network analysis that if there is a high resistance, okay, and there is a low resistance, short circuit, right? And if there is a current, right, so this entire current will follow what? The minimum resistance path always, right? So this I in will be equal to Is then, right? So what we can say that your R in should be far less than Rs, or you can say that your R in should be what? R in should be low. Okay, this is our requirement, and according to our requirement we are able to decide the input resistance of the current control current source, and according to our requirement we will be able to decide the output resistance of current control current source. So here you can see we want I out equal to K times of I in, means that this entire current should flow through this, right? So R out should be very high, means it should be open, right? So we can say that R out should be far greater than RL, right? Or you can say R out should be high, right? Right, so R out should be very high. Okay, so I hope this is understood. So you are able to decide, right? You are able to decide what output resistance and input resistance, right? So current control current source, right? This was the second kind of amplifier. From here we have seen AI, that was I out upon I in, right? That was a current gain, right? And this part is known as source, and this part is known as what? The amplifier, and this part is known as load. You can say this is I out only, right? Here you can again see I out is what? The independent of the load resistance RL. Okay, this is very important note, right? And what is the value of R in? R in should be low. What is the value of R out? It should be high. Okay, and you can also keep in mind that if there is a current source, so current source will be having internal resistance high always, right? So this is one kind of convention you must keep in mind, right? So if there is a voltage control, means Rin should be what? High. If there is a current control, Rin should be low. If there is a voltage source, R out should be low. If there is a current source, R out should be high, right? So in this manner you have to tell any kind of amplifier. You can decide the input resistance or output resistance, or if you're looking at the data sheet, right, some specifications are given regarding regarding amplifiers, right? So you will be able to decide what kind of amplifier they are talking about, right? Okay, so what are the things you need to remember here? Current control means input resistance will be low. Current control input will be low, despite it is a current, but there is a control word associated, right? You have to keep in mind that it is not a current source kind of a thing, right? It is a current control. So this was the requirement, and according to requirement we decided Rn should be equal to 0, right? Ideally, we can say ideally, and current source is there, means infinite, so we can say high, right? This was the requirements, right? I out equal to K times of I in. Okay, right? So what are the examples of current controlled current source? Here there should be current control current source. Remember, current control current source, right? So the common base amplifier, okay, mimics the property of current control current source, right? So you have to keep in mind that current control means looking at the value of the resistance. Here you can see, forget about this symbol, right? If you are not able to understand this symbol, it's okay, but look at the input resistance and output resistance, right? So this is what, okay, and here it should be in mega ohm, right? It should be in mega ohm, right? Okay, there should be one correction, it should be in mega ohm, right? So current control low resistance is there, that's why we are calling it current control, right? And 1 mega ohm resistor, mega means high resistance, right? So current source. Okay, and you know that common base amplifier, or common base means that we will talk about bipolar junction transistor, right? So any bipolar junction transistor, if we will talk about in future the output IV characteristic of that amplifier, right? So we will try to achieve this kind of characteristic, right? So this is the ideal characteristic of a current source. We know that any ideal characteristic of this is the ideal current source, right? Suppose IS, right? And if there is no resistance, right? So whatever voltage you are applying here, suppose you are applying here, this will always maintain its own terminal current, right? This is what the property of ideal current source. You might have studied in network analysis. So you are changing the voltage here, but your current is constant, right? This kind of property we want, means that my collector current should not vary. In future we will study in bipolar junction transistor, we will try to refrain that, or we will try to free collector current variation from any other parameter, right? Suppose any other parameter is varying, so my collector current should not be depending upon them, right? So we will try to model the current sources, try to model the practical current sources or the ideal current sources, right, in entire analog circuit. So there will be two jobs: design amplifiers and design good current sources. Okay, right? So the common base amplifier will be treated as current control current source. And now you know how we are claiming that common base amplifier is treated as current control current source, depending upon the input resistance and output resistance. Okay, right? And the third kind of amplifier what we are supposed to discuss here is the voltage controlled current source, right? The voltage controlled, in the input voltage signal is there, in the output current signal is there, right? Okay, so there is voltage signal V in, and there is there is the output, that is I out, and I out should be what? K times of V in, right? What is the dimension of K here? K should be equal to I out upon V in, right? I out upon V in. What is the dimension of K now? The current upon voltage. As we know that from network analysis, again, current or ohm, from the Ohm's law, right? Current upon voltage will be what? The conductance, right? The dimension will be conductance. Okay, moho, or you can say opposite of resistance, right? And why we are calling it trans conductance amplifier, right? Why we are calling it trans? Because the input voltage is being converted or transferred to the output current, right? Remember, you are applying input voltage and it is going to be converting into current, right? So we can say it is a voltage to current converter, right? So with the help of any op amp we can implement, right? With the help of op amp and connecting resistances, we can build a kind of amplifier, right? In the question also, in the gate examination, they ask questions from voltage to current converter. They will give you some circuit, right? And you have to find some output, right? So you always apply KVL and KCL. Okay, so but you don't understand what is given in the circuit. But in the examination, if you are able to understand, or able to identify this is a transconductance amplifier, right? Okay, so you would be able to answer questions very quickly, right? Okay, so voltage controlled current source means what? Transconductance amplifier. And GM is the transconductance parameter. Okay, it is one of the very important parameter which you will find always in the gain expression, right? So any amplifier is there and the gain expression is minus GMRC, right? So what is GM? GM is the transconductance parameter of the transistor, or GM of the transistor, right? Okay, here current source is there. Again, from this arrow you can understand this is a current source and this is a voltage controlled current source, right? And this must be equal to GM times of V in, means this case should be equal to GM, right? Okay, so this is our requirement here. Again, we can draw the input signal should be what? Voltage control means voltage, so we need to use what? The Thevenin equivalent, right? This is voltage and this should be RS. Okay, and there should be what? Let me use different color again. So input resistance should be there, right? R in. Okay, and there should be what? Or you can use diamond shape here, right? Just use diamond shape. Okay, so diamond shape is gonna be your current source only, right? K times of V in, because we will apply the voltage signal here. This is the input voltage. Okay, input signal to the amplifier here, and output resistance should be connected across this current source or out, and RL should be there, right? Now by looking at the by looking at the name of the amplifier, you can decide, okay, what can be the input resistance, what can be the output resistance. As we know that voltage control means Rn should be infinity or high, and there is a current source means it should be high, right? So many times this question has been asked in the gate examination, in fact 5 times, or in different IS IS examination or ISRO examination. This kind of question you can expect. The transconductance amplifier, what is the input? Okay, what is the input resistance of transconductance amplifier? what is the output resistance of transconductance amplifier, right? So we know that transconductance amplifier is what the VCCS, right? Means your voltage to current converter kind of amplifier, right? So this is V out, I mean Rin should be high here, right? Because voltage control is there, means Rin should be high and R out should be high. So transconductance amplifier means high. You have to keep in mind this kind of terminology, high sir, okay, right? So this is how your transconductance amplifier look like, okay? So here you can see this is a signal part, right? The source part, the microphone part, right? And this is going to be your amplifier part, and this is the load simply, right? And here I naught is always independent of this load RL, right? Okay, so what we can say here is that according to our requirement you can decide that, okay, if there is a VC means Rn should be high, okay, you can say there will be V in here, okay, this Rn you can connect here as well, no problem, right? And this R out should be what? R out should be again high. Why? Because we don't want any current to flow through this R naught. Entire current should flow through this I naught, right? I mean this RL. So I naught will be equal to GM times of V in. Okay. Right. So I hope this is understood for you. You can easily decide the input resistance of transconductance amplifier and the output resistance of transconductance amplifier, right? Okay. So you have to keep in mind these 2 points. The voltage control according to our requirements, this is high, sir, right? Ideally, and this should be high, sir, again. I naught should be GM times of V in, or you can say I naught upon V in is the GM, right? It is not the gain, basically it is a transconductance parameter of the transistor. It is very important, and you will find in all the gain expressions like GM RD, GM RC kind of, okay? There is a current source, that's why output should be high, right? Okay, so what are the examples of voltage control current source, right? Voltage control current source, right? So voltage control means input signal is a voltage and output signal is a current. So field effect transistors, right? Field effect transistors basically you can say mimic the property of transconductance amplifier or voltage control current source amplifier, right? Okay, and operational transconductance amplifier, OTA, okay, they are also known as OTA, right? Operational transconductance amplifier, or you can say voltage to current converter implemented using op amp, right? Voltage to current converter implemented, okay, using op amps. In future we will design them, right, and solve questions as well, right? So OTA, right? So these are the 2 basic examples which you must know, and depending upon its input resistance and output resistance you can decide, right? Okay, current controlled voltage source, it is the last kind of amplifier, right? So we have been talking about 4 kind of amplifier. 3 amplifiers have already been discussed, and you know that how to design, how to draw the equivalent of those 3, and how to decide input resistance and output resistance according to our need, right? Okay, there is no formula to remember if there is a need, okay? So as we know that necessity is the mother of invention, right? If there is something we want, so we need to invent, right? Okay, so current control voltage source. Current control means input should be current, and voltage source means the output should be voltage, right? Okay, so here the voltage output should be voltage, so K times of I in we want. We can say that K must be V out upon I in, right? So what is the dimension of V out upon I in? Means the voltage upon current, means this is gonna be your Rm. You can say the resistance. And what kind of resistance I'm talking about? Trans resistance, right? Why? Because the current is being transferred to the output, right? Trans resistance, transfer from one port to the another port, right? Any amplifier will be having 2 ports, right? I mean input port where you're going to apply the input and output port there where we are going to get the output, right? And there will be another ports, right, power ports and all. Okay, we will discuss, okay, when we will discuss actual amplifiers, right? Okay, so this is how the current control voltage source look like, what you might have seen in the network analysis, right? So after all, this is a voltage source and there is a controlling parameter, right? It must be current here, I in, right? I in, okay, it must be I in. So V out should be equal to Rm times I in, okay. Okay, so let us draw here the model again, or draw the equivalent current controlled, right? So input signal is going to be current signal, so we need to use Norton equivalent here, okay, and there should be Rs, okay, this is going to be your Is, and there should be you know, Rin, amplifier resistance, okay, okay, this is I in, right? And there should be what, the voltage source plus minus, you can say V Rm times or K times, or you whatever you want to call it, right? Rm times, and there should be R out, and there should be RL, RL, okay. So you can easily decide what exactly you want, right? So as we know that current control means input resistance will be low, okay. As we know that voltage source means output resistance will be low, means it will give you low resistance, right? So depending upon the resistances also you can classify the amplifier, right? Okay, we will see that in the summary. So current control current source, right? Current control voltage source, sorry, it is a current control voltage source, right? So it is also known as trans resistance amplifier, right? Depending upon the dimension of the K, okay, and this is going to be your actual equivalence, right? So from here to here you can see, and if we want I in should be equal to Rs, so this guy should be what, low, okay. And if we want this V out should be equal to R in, so this guy should be low, okay. This should be equal to Rm times I in, right? This should be Rm, right? Okay. So this is the load, and this is how we represent amplifier with the help of these dependent sources, and this is the source, right? Okay. So these are the points you need to remember. Current control, Rn should be low, okay, ideally, or 0 you can say. It should be 0, low. I mean, this is practically, right? This is ideally and this is practically, you can say, okay. And these, according to our requirements, we are doing all these things, right? Okay. So Vs, if there is a Vs, definitely R out should be low, right? It's okay, because source will be always connected to the output port and controlling parameter will be present in the input port. You have to keep in mind these things, okay. Right. So what are the important examples of current control voltage sources? Somebody is going to ask you. So you can say that current to voltage converter, right? So if you will find this kind of a topic, so now always it will hit you. Okay, sir has discussed in the class. Okay, or you will see the circuit, right? So you will be able to identify. Okay, this is a current control voltage source, right? And it will give you trans resistance, right? Okay. So this is one example, current current to voltage converter implemented using op amps, right? Okay, so we'll see how to design all these things in the future classes, okay. Right, so this was all about 4 kind of amplifiers, right? And we have modeled all those 3 blocks. We started with microphone, we you know, then go bend to amplifier, then load, okay, and we modeled all those things, microphone, amplifier and speaker, okay, and we have drawn the equivalents, okay, and based on the need of based on the requirements, right, we decided the input resistance and output resistance, okay. We classified earlier based on the nature of the input and output signal, right, the 4 kind of amplifier. Now we are ready to what, classify the amplifiers based on its input resistance and output resistance, right? This is going to be your input resistance. So let me change the color here, input and this is going to be your output. Okay. So if it is a voltage control voltage amplifier means VC VS, right? So high and low. Why? Because VC, right? VC means high and it should be low. It will give you what? The voltage gain. These are the parameters we are going to see. If this is a current control current source, right, means current amplifier, so it is gonna be giving you what? Okay, resistance should be low and high. So this is just like a binary pattern, 0 1 1 0 kind of, right? So you have to keep in mind like this table you have to build in your mind, right? So what you have to do, voltage amplifier high low, okay, current amplifier low high, trans conductance amplifier high high, trans resistance low low, right? So you can better decide, right? So see, I out upon V in. Transconductance means what? Output current upon input voltage. So you can say that it must be voltage control current source. It must be current control voltage source, right? So these are the four kind of amplifier what we have summarized, and based on the input resistance and output resistance, you can claim back that these are the amplifiers. So if you will look at the data sheet, input resistance, output resistance, or in your gate examination actual questions, so depending upon looking at the input resistance and output resistance, you would be able to decide, right? So in the examination they will give you any amplifier is there, it has this gain, okay, and it has input resistance and output resistance. Another amplifier is there, it has this gain, this much gain, and input resistance, output resistance. So find the overall gain, right? So there will be two blocks, okay, so you will cascade them, right? You will connect all these equivalents, you have to draw these equivalents, then apply some voltage division or a current division rule, and you will be able to find the overall gain, right? So we will talk about in future, okay, amplifier in detail. So this was all about amplifier modeling. I hope you might have understood. Okay, so thank you.